Assalamu alaikum, dear students. In today's lecture, we are going to discuss about a very famous encryption scheme that is known as Advanced Encryption Standard or AES. And because of the insecurity of data encryption standard, it was officially replaced by Advanced Encryption Standard back in 2001. So in 1997, the data encryption standard was actually broken, and this happened because it had a very major vulnerability that was a 56-bit key. So back in the 1970s, this key was considered to be very secure, and rightly so, but this key space became too small as computing power increased. So in 1997 to 1999, the cryptographic community proved data encryption standard was unsafe through a series of data encryption standard challenges. In 1997, it took several months to break, but by 1999, the distributed computing efforts broke it in less than 24 hours. And specifically, Deep Crack 1998. So the Electronic Frontier Foundation, they built a custom machine which they called it Deep Crack, and they built it for $250,000. It was a specialized machine which whole purpose was to break the DES, and it broke DES encrypted message in just over 2 days, and which basically showed that an inexpensive hardware, yes, inexpensive, it is cheaper as compared to what you are breaking, right? So an inexpensive hardware could easily compromise it. So this device was specifically designed to break this data encryption standard. Right. So next we are going to discuss about key differences between AES and feature structures. So as we know that most of the block ciphers are based on feature structures, and the prime example is data encryption standard. So what are the key differences? So basically the feature structure, the major difference is that it splits the block into two halves, right? And you only do processing on one half, and the remaining half is transferred to the next round without any changes, right? As compared to AES, it is based on SPN structure, substitution permutation network structure, and it will process the entire 128-bit block as a single 4 by 4 matrix of bytes in every round. So it does not divide the input into two halves. In fact, it processes the input at once, right? The second major difference is invertibility. As and you know that invertibility means that you can reverse the function. So the round function that we are using in data encryption standard does not need to be invertible, and the exclusive OR operation ensures reversibility. So the round function is not invertible. Doesn't mean that you cannot reverse it. Obviously, you can when you are doing the decryption, so you reverse the whole process. So what actually is meant by this statement is that the round function is deterministic. Like for the same input, the output should be same, right? So if you provide the same input, so the output is again calculated as same, and you are using this exclusive OR operation which is ensuring the reversibility. As you know that if you do the exclusive OR twice, so then you recover the original thing, right? And on the other hand, in AES SPN structure, and this SubBytes, and you will see that there are different steps in it, and each and every component of AES is individually invertible for decryption. So that's another major difference. And in S boxes, they can be non-invertible, so it's not recommended. In case of DES, obviously it was non-invertible. I'm going to talk more about invertibility in the next slide as well. And so in comparison, in AES, the S boxes must be invertible, right? To allow the inverse SubBytes steps during the decryption. Forget about these confusing terms. We are going to see them one by one. So the S boxes are invertible. Decryption in AES, it uses the same algorithm for encryption and decryption, right? Sorry, in DES. On the other hand, in AES, you require two different algorithms. Because the second algorithm will be using the inverse of those functions, so you need two separate algorithms. When it comes to efficiency, so it is often slower in software due to bit level operations and lack of parallelism. On the other hand, AES is designed in a way that it is very hardware friendly, and it also operates on full bytes and also allow for parallel processing. So now let's discuss about the invertibility thing a little bit more. And here I would also like to suggest you to read DES because we covered the major aspects of the DES, and but we did not go into the very details. So in the book you can perform very simple mathematical things to, for example, to show that the the encryption of one round is exactly equal to the decryption in the corresponding round in the decryption side, right? Basically, invertible function is a function that can be reversed to get back the original input. So, for example, you can mathematically you can write it as f of x, and if you take inverse, and then you get the x. So, below are some examples. For example, you have a function which does x plus 7, right? So, if the x is 5, so you get 12, right? So you can have another inverse of this function like x minus 7, and if you provide the same x, so it will again give you 5. So the 5 is recovered, right? Similarly, the multiplication 3x, and the inverse would be x by 3. So again the x is 4, and then you reverse it and you found the x equal to 4. Similarly, exclusive OR function, which is a very common in cryptography. So this is x exclusive OR k, and let's say that your x is 10 and the k is 5. So encryption 10 5 means 15, and when you do the decryption, so then you take this 15 and then you take the key which is 5, and then you recover the original one. So applying exclusive OR with the same key returns the original value. So it is invertible. So what is not invertible function? In non-invertible, the most common example is x square, because if the output is 9, so the input could be 3 or input could be minus 3. So we cannot know the exact original input. So hence the function is not invertible. Uh, when we talk about DES, so we often talk about S boxes. So is S box or the S box is invertible or not? So you can simply it's very simple to see them. If you remember, the input to the S box was 48 bits, like, and we were using because it uses 8 S boxes. So each S box, the input was 6 and the output was 4, right? So each S box takes 6 bit as input and it produces 4 bit as output. So the from input side, the total possibilities are 64, and from the output side, the possibilities are 16. So 64 bits are going to be mapped to 16. So which means that you are going to lose information. So this means many different input produce the same output, obviously. So it is not invertible. So now we are going to talk about advanced encryption standard, and now you already know the main difference between advanced encryption standard. You know the main difference between crystal structure and SPN network. So if someone asks you the question, or just keep in mind that what is the major difference? So the crystal structure, it divides the input into two halves, and then one half is left is goes to the next round unprocessed, and the other half it goes to the processing, and each round you do substitution and permutation. On the other hand, in SPN networks, you process the data together, do not divide it into two halves, right? And it also has rounds, and in each round you also do substitution and permutation, and you do it iteratively, right? So And the other major thing is that each and every component in SPN networks is invertible. On the other hand, in data encryption standard, it does not have to be true, right? So advanced encryption standard was designed by two Belgian cryptographers named uh, Ryman and Damon. So they were professors in a very famous lab or the research unit known as COSIC in Catholic University of Leuven. So let's slowly discuss about the features or the parameters of the advanced encryption standard, and then we will go into the details. So the block size in advanced encryption standard is 128 bits, right? So that is going to be your plain text, right? And you can also write this 128 bits as 4 words or 16 bytes, right? 16 bytes. So either 128 bits and or 4 words. This each word size is equivalent to 32 bits, right? So 32, 32, 64 plus 32, 96, and then 128. So you can also use the terminology 128 bits, or you can use 4 words, or you can also say 16 bytes. Uh, so in AES, the terminology of word is used very commonly. So the total number of rounds in AES are 10, and the key size is 128 bits. That is 4 words or 16 bytes. And so then you will also have a number of sub keys, right? And the total number of sub keys in AES is 44, right? And each size of the each sub key. So each sub key will be 32 bits long, right? 32 bits or one word or 4 bytes. So again, I'm telling you that the block size is 128 bits. Number of rounds are 10. The key size is 128, and from this key size, basically, you will generate uh, more keys. So they are known as sub keys, and there would be total of 44 sub keys. 44 sub keys, and each sub key is 32 bits, right? So let's see other. So each round we will use 4 sub keys. So there are 10 rounds, so 10 into 4, 44, right? So each round you will use 4 sub keys, right? And before the rounds, you also have another block which is called pre-round calculation. Pre-round calculation, and it will also use 4 sub keys. So again, you have the 10 number of rounds, and each round is using 4 sub keys. So 10 into 4, 44, and in pre-calculation block, you are also using 4 sub keys. So 40 plus 4, that is 44, and that's why it says that you need 44 sub keys. So the total number of keys are 10 plus 1, that is 44 keys. And the cipher text is going to be 128 bits. So the plain text is 128 bits. The total number of keys are 44. Total number of rounds are 10. And the cipher text is 128 bits, right? Now we are going to see the encryption process. And so encryption process, so what happened is that so you see that you have a plain text which is 16 bytes or 128 bits, right? And first it will go to add round key. So we will later see that what is add round key. So basically it is just an exclusive or but we will see later on. And the output of add round key will go to substitute bytes. Then the output of substitute byte block will go to shift rows, and the output of shift row would go to mix columns, and the output of mix column would go to add round key. So this four steps, these 4 steps is called round 1. Again, I repeat that substitute bytes, shift rows, mix column, add round keys. So you see there are 4 processes in this. So these 4 steps are called one round. And then you do this in the second round, you do the same thing. And also another thing that you see here is the you have the key, which is 16 bytes, that is 128 bits, and you expand this key and you make 44 keys out of it. And the first 4 keys here, it is representing as 0, 1, 2, 3. So here 0, 1, 2, 3 is collectively called as K1, right? The first key. So that will go to your round key. And the next 4, 5, 6, 7, 4, 5, 6, 7 words, right? So basically each word is 32 bits, so 32, 64, 96 and 128. So that will be your key 2, and it will go to this round 1, right? And then similarly you will have the round 2, the same process, the round 3 same process, the round 4 same process, and in the round 9 is the same process. Substitute bytes, shift rows, mix column, add round key, right? But for the last round, which is the 10th round, you do not have this operation, mix column. So here if you see, you only have 3 processes. You only have 3 processes. Substitute bytes, shift rows, add round key, right? So I repeat it again that your plain text is 16 bytes or 128 bits. It first goes to add round key, and then it goes to round 1, and round 1 is based on substitute bytes, shift rows, mix column, add round keys, and then you repeat this 4-step process for the next 9 rounds. And for the very last round, you only have 3 processes. There you don't have the mix column step. And on the right side you are seeing that the your key is like 128 bits, and you expand the key. Later we will see that how we are going to expand the key. So your first key will go to round 1, second key will go to the first key would go to add round key, the second key would go to the round 1, the third key will go to the round 2, and the last key, which would be the 4 words 40, 41, 42, 43. Remember I told you that you have the 44 keys in total, 44 sub keys. So here the K1 is collectively referring to the 4 words, right? So the key 0, K1, K2, K3, it is collectively called as K1 here, right? So so that's your encryption step. So now let's see that the whole diagram. So here it is showing you the whole diagram, the similar one. So here you are seeing this round 1, and then the same thing happened in the round 9, and the round 10 you just don't have the mix column step, right? And if you see the decryption, so it is just it looks similar, but actually the many of the stages have their own reverse. As I told you that all the components are do have their inverse. For example, you have this ciphertext. Ciphertext goes to the add round key, and then you have this inverse shift rows. Then you have this inverse SubBytes, and then you have add round key, and then you have inverse mix column, and similarly you have this in the very last round you have this inverse shift rows, inverse SubBytes, and add round key. So the last round has only 3 processes, and the all other rounds have these processes, four processes: inverse shift rows, inverse SubBytes, add round key, and inverse mix columns, right? So let's move forward. Here I am going to show you the representation before we discuss about the each and every part individually. So first I will show you that how the advanced encryption standard the information is represented, right? So as I told you before that we are going to use the terminology of words, right, in this. So initially you have the input, which is 128 bits, 128 bit input, and you will arrange this input into a matrix, and this matrix is 4 by 4. This matrix is 4 cross 4, right? So here you see that the input 0, and then you will arrange this input in column wise, right? So input 0, input 1, input 2, and input 3. So this input 0 is your first byte. It's your first byte. The second byte is called input 1. The third byte is called input 3. The fourth byte is called input 4. So in this column, how many bytes you have? 8 bits, 8, 8, 8. So that is 32. So this 32 bits, total of, let me write here, 32 bits form a one word, which we call it word 1, W1, right? And similarly, you have the input 4, input 5, input 6, input 7, and this form a word 2. Then you have word 3, and then you have a word 4. So it is a column major representation of the matrix. It is a 4 by 4 matrix in which you will first write word 1 in the first column, word 2 in the second column, word 3 in the third column, word 4 in the fourth column, and each cell contains one byte, right? So this will be your input. So the next is your intermediate results. So after you do some so you have a plain text, and after you do some kind of processing, so it will store the results in a state array. So in state array, you will be using this kind of representation. So basically the input 0, 0, 0, this byte would become S0, 0, right? And then S1, 0, S2, 0, and then S3, 0. And this will be your first word, right? So basically, and similarly, 0, 1, 1, 1, 2, 1, 3, 1, 0, 2, 1, 2, 2, 2, 3, 2, 0, 3, 1, S1, 3, S2, 3, and S3, 3. So each location is one byte, and this means that the first byte of first word, and this means that the second byte of first word, and so on. And similarly, the output would be 128 bit as well, and for output we will use out 0, out 1, out 2, out 3, and this each cell is 8 bits or 1 byte, and the total of 32 bits, right, or 4 bytes, and this will form as the first word. So this is the representation that we are going to use in advanced encryption standard, right? So next about the key. So the key is exactly the same, like 128 bit keys, or you can say 4 words. And so this is how your key is going to look. So you have K0, K1, K2, and K3, right? Okay, so that will be your word 1, and then you have K4, K5, K6, K7, that will be your word 2, and K8, K9, K10, K11. So this 8 bit, 8, 16, 24, 32, that is word 3, and your word 4, which is K12, K13, K14, and K15. And so this is your 128-bit key, and then from this 128-bit key you need to generate 44 subkeys 44 subkeys W0 till W43. So this W0, that is the first word, the 2 bits, W1, W2, and here you can say that W3. Okay, so this W0 till W3. So the terminologies can get confusing. So basically, this key is the first key. So here I am also using K1. So this terminologies can sound confusing. So these 4 words basically will be the first key which is used for the add round key, and the next 4 words that are W4, W5, W6, W7, they would be the second key and they will be used in the round 2. And similarly, you have the 44 subkeys. So I hope it is sufficiently clear now. So now we are going to see uh, the the 4 transformation that we discussed. So as I told you that in each round we are using 4 processes, and now we are going to see each process one by one, right? So we are going to start with substitute bytes transformation. So that's our first process, substitute bytes transformation. It is actually what it does is that it substitutes the bytes and it uses SBox. So let's see what it's saying, that the forward substitute byte transformation is called SubByte. So in short, you will call it SubByte, and it is a kind of lookup table. You know the lookup table, that you have the address and then you find out what that address contains. So AES defines a 16 by 16 matrix of byte values known as SBox. So if you recall, in data encryption standard we had 8 S boxes, and in 8 S boxes, so each S box was taking in 6-bit input and producing 4-bit output, right? So unlike data encryption standard, here you have a full 16 by 16 matrix, and each cell represents a 1 byte, and which means that it contains permutations of all possible 256 8-bit values, right? And each individual byte of state is mapped into a new byte, right? Remember the state array that I told you that, so before that, so your input is coming and then you will store it into input matrix, and then you will process it through AddRoundKey, and we are going to see what is happening in the AddRoundKey as well. And then its output is called, and then you store the output in a state matrix, so that state S00, S01, so on, right? So it's very simple. So you have the uh, 8 so basically in your byte you have the 8 bits. So the left 4 bits of the byte are used as a row, and the rightmost 4 bits are used in the column value. So you will have your state matrix as an input, so which is basically the output of the add round key. Remember that you have the pre-calculation round. So in your pre-calculation round you have the output, right? And that output would be uh, basically a state array, and in this state array each location is basically a 1 byte, and then in 1 byte you have 8 bits. So the first left 4 bits of the byte are used as a row value, and the right most 4 bits are used as a column values. So these row and column values serve as indices into S box to select a unique 8-bit value. So here is how it happens. So you have the S box. There is your S box, right? This is a 16 by 16. So 16 rows and 16 columns. And let's say that this is your state array. And here S11. So S11, which is a byte. So you go into the corresponding X location, the first 4 bytes, so the left 4 bits will select the row, and the right 4 bits will select one of the column among it. And let's say that in this example it is showing that it has selected this column, and then this value will be replaced with another byte, with a byte that was stored in at this location, and now it is called S prime 11. So from S11 it has become S prime 11. Let's see a more. So this is your S box. So as you can see that in your S box you have how many columns? You have 16 columns, right? Marked as 0 till F, 0 till F, and also you have 16 rows, right? Starting from 0 till going all the way to F, right? So 16 rows, 16 columns, which means that you have total of 256 possible elements in there. And it's actually very simple. For example, you have this, the input is 95 in your straight matrix, 95. So it means that first 4 bits mark the rows. So go to the row number 9. Okay, the row number 9 is selected, and the column number 5. So row number 9 and the column number 5 is, this is your column number 5, right? And row number 9, so you have 2A. So this 95 will be replaced with 2A. So 95 is going to be replaced with 2A, right? Okay, so let's move. So here it is telling you the same example that I just showed you, that this 95 is replaced with 2A, right? Accordingly, you can do it yourself, that if you have this state matrix, and in each matrix each cell is 1 byte, so then you can just go to the S box table and then see the E would be the row and A would be a column, and then this would become 87. Similarly, you can do this for all uh, elements, right? So it's very simple. So it's just the substitution, right? So the second step after your S box or sub byte is the shift rows. So remember, the output of these sub bytes or the substitution will be used as an input to the shift rows, right? So again, this is your straight array, right? So let's read the theory, that the forward shift row transformation, or simply it's called shift rows, is depicted in figure 6.7a, right? So the first row of the state is not altered, so you will not change this first row, right? And in the output you see that it is going to be the same, S00, S01, S02, S03. For the second row you will do 1 byte circular left shift, right? 1 byte circular left shift. So which it means that the S11, it will come over this position, right? And here in output you see that S11. Similarly, this S12 would go into this position, and you see S12, and the last one is S13 will go into this position, and here you see S13, and obviously because it is circular, so the last one is S10. So you are just doing a 1 byte left circular shift. Similarly, for the third row, you will move 2 bytes. So by 2 bytes mean that this S22, it will come into this location, right? S22 will come there. Similarly, the rest of the 3 you can see. And for the fourth row, you will do a 3 byte left circular shift, which means that this S33, it will come onto this location, right? And this S31, it will go to this 1 2 3, and then this will come into this location here, right? So similarly you can verify for all others as well, right? And another important note to take is that since the state is processed by columns, and you know that this is the word 1, and this is word 2, this is word 3, and this is word 4, and the state is processed always by columns. So this step permutes bytes between the columns. So that's the rationale behind it. So moving it, so you are basically disturbing the value in different words. And when you are doing the decryption step, so you will just do the inverse of this thing. So just rotate the byte one so 1 byte right circular shift, 2 byte right circular shift, 3 byte right circular shift. So so this is how your table will look, and here it is showing you one concrete example. For example, this first row is unaltered, it's not changed, 82 87 52 4D 97. In the second you see that the 1 byte left circular shift, so that your uh, EC has gone into this location, right? And your CE, which was in the second location, has moved into the first location. And similarly you can verify for all the rest of, for example, in this one, so for the last row there was the 3 byte left circular shift, so A6 has come into this position. And for the inverse shift row transformation, it is called inverse shift rows. You just need to perform a circular shift in the opposite direction for each of the last 3 rows. The first row would be left unchanged. Okay, so this is your row transformation. So the output of your row transformation will go to the next step, which is mix column transformation. Mix column transformation, right? So let's first read the theory, and then we will see a concrete example as well. The forward mix column transformation, called mix column, it operates on each column individually, right? So each byte of a column is mapped into a new value that is a function of all 4 bytes in that column. So we will see that. So in this mixed column transformation, you have a one fixed matrix, and that is always be fixed. So it has 4 rows and 4 columns, so it is 4 by 4, and its values are 2 3 0 2 3 1 1 1 2 3 1 1 1 2 3 and 3 1 1 2. So that is a fix, that is a constant, it is provided, right? And then you will have your state matrix, all right, which is the output of the last step, which was shifting of the rows. And then you will have an output, right? So in which each byte would be changed as 00 has become as prime 00. And it is also telling you that all 4 bytes in that column, um, basically each byte of a column is mapped into a new value that is a function of all 4 bytes. So as you will later see on that, this value depends on all 4 values in this column, S00, S10, S20, S30. And this matrix multiplications, so in AES we perform the mathematics in a Gauss field with a polynomial with a degree of 8. So since I told you that we are not going to solve this algorithm by hand, so that's why I'm not going to teach you this mathematics, how the mathematics are done in Gauss field. Those who are interested, it's not very difficult. You can read chapter number 5, so in which you can see that how the mathematics are done. So the addition, multiplications are performed in Gauss field. So right. And especially in Gauss field, they are using 2 to the power 8, the polynomial with the degree 8, right? But you are not supposed to solve this by hand, so you can skip this part as well. But if you are interested, you can read it, right? So let's show you one more angle. So you have this state array S00 in which the first word is S00, S10, S20, S30. So that is your word 1, which is the output of the last step. And you have this a matrix, 4 by 4 matrix with the values predefined, right? And here what you do is that you will take this word, the first word, S00, 10, S20, S30, and you will put it there. So I just you will take this column and you will put it here, right? And that will have 4 rows and 1 column, so that's why I have written it 4 by 1, and this matrix is 4 by 4. And you know the matrix rules that the number of columns should be equal to the number of rows, then the multiplication can happen. So the result would be 4 by 1, so another column. So this will be your result, and this result will be placed in the first column of your state matrix. And now here you can see that they have S00 has become S prime 00, S100 has become has S prime 10, right? And similarly, then you will take this second word. As I told you before that in AES we process on the words. So you to take on this second, sorry, this is your word number 2. Pardon me for my writing word 2, right? So word 2, you take this word, now you put it in here, and again you multiply this with matrix, you get another result 4 by 1, and you place it in the second. Similarly, you do this for third, and you do this for fourth. I'm going to expand a little bit more on it to show you how each value is actually dependent on the 4 values of that column, right? So we are going to see that. So for now, just remember the first 2 3 1 1. Okay, so here is how it is going to happen. So it's a simple matrix multiplication, but here the rules are changed. So you need to calculate this multiplication, and instead of addition, we are going to use exclusive OR. And again, all this is done in Gauss field, which we are not going to study. And so this the first term is 2, which is multiplied by S00, and then 3 will be multiplied with S10, right? And then 1 will be multiplied by S20, and then again 1 will be multiplied by S30, right? So 0010, S20, and S30, right? So these are all the bytes in your first column. So if you add them here, we will do the exclusive OR, then you form this S-0, and similarly you do this for S10, S20, S30, and that's your column number 0. Then again you do it for column 2, then you do it for column 3, and then you do it for column number 3 as well. So 4 columns. So that's your mix column step. And here it is showing you an example that after the transformation, this is how it is going to look like. Again, those who are interested in solving by hand, they can read the chapter number 5 and see how the Gauss mathematics work, Gauss fields work. Sorry, Gauss fields, mathematics in Gauss fields work. And also in appendix, there is a simplified version of the AES, and when you understand the bigger version, so and then you study this simplified version, so then it becomes very easy. And the practice has shown that after reading the bigger version, then the smaller version, and then you read the bigger version again, so the concepts are more clearer. So right, now we are going to see add round key transformation, which is the basically pre-round calculation. It's a very simple thing, and that was the first thing that we saw in the table, and it is actually exclusive byte-wise exclusive OR basically. So you have this input matrix, right? You have this input matrix, and you have this key, right? And then you have the state. This will be your state. Uh, State, I can write it as here. Okay, so what happens is that you are just going to exclusive OR. Again, the operation will be performed column by column, but you can think of it as 47 exclusive OR with AC. It has become EB. That you can easily verify by pen as well. So the first matrix is the state, the second matrix is the round key, right? And then you have this output, which is also a state as well. So, and when you are going to inverse it, so basically you use the inverse add round key transformation, which is identical to the forward add round key transformation, because the exclusive OR operation is its own inverse, as we saw in the previous slides. So what happens here, it is just telling you that, for example, this second word, right, is exclusive OR with this second word, and then you have this exclusive OR result, right? So that's how add round key transformation. So basically you can think of it as a Vernam cipher. So it is just exclusive ORing each byte individually. So the last part of AES algorithm is the key expansion. So as I told you before, that you have one master key, which is a 128-bit key, or you can think it of 16-byte key, and from this key you need to produce 44 keys, right? 44 keys, or you can say that you need to produce a linear array of 44 words. 44 words, 44 words means 176 bytes, and in each round we are going to use 4 keys, right? So word number 0, word number 1, word number 2, word number 3, that would become a first key, which is going to be used in the add round key. And then word number 4, 5, 6, 7 for round 1, and then 8, 9, 10, 11 for round 3, right? And so on. So what happens is that the key is copied into the first 4 words of the expanded key. So first you need to copy your first 4 words, which is the original key, into the of the expanded key. The remainder of the expanded key is filled in 4 words at a time, right? So how? I'm also going to show the algorithm as well, but let's first see the theory, that the each word wi depends on the immediately preceding words, so that we can write I minus 1, right? And the word 4 positions back, I minus 4. So the each word, the next, so the first 4 words are just copied, right? So the each, then the, for example, the fifth word, it will depend on the previous word, the fourth one, and on the previous 4 words, preceding 4 words. And again, another thing is that in 3 out of 4 cases, you will simply use exclusive OR, right? And for fourth case, what you use is that which would be the multiple of 4 actually. You will use a very complex function, right? So figure 6.9 illustrates the generation of expanded key using the symbol G to represent a complex function. So again, let's first see the algorithm and then we will also see the figure as well. So what this slide is telling you that you have 128 bit keys, 128 with the original key. You need to form a 44. Basically, 128 bit means 4 words, and from these 4 words, you actually need to develop or expand it to make it 44 words. And so how do you do that? So the first 4 words are copied as it is, and the next few words are copied as per this logic that each word would be dependent on the preceding word and also the 4 positions back. And then in the 3 out of 4 cases, that which means the 3 words will simply be formed with the help of XOR operation, and the fourth word would be formed with the help of a complex function which is called as G, and that would be actually a multiple of fourth position. So let's look at. Okay, so there was some error that it looks like I cannot remove this text from here. So I'm going to just move to the next slide. So this slide is the actually the replica of the previous slide. So here it is explaining you the pseudo code, and so what happening is that you have this array which stores the key. It has 16 bytes, and then you have another array word which has 44 words. So it's very simple logic here. So first in this step, your loop runs for 3 times, right? And in this first portion of your loop, what you are going to do is that you just need to copy the original key into your word array, right? So for I equal to 0, you can also run it for yourself, but just I'm going to explain so that it becomes easy for you. So for I equal to 0, that would become W of 0, right? Pardon my writing, W of 0, and this one would become key 0, obviously, and this would become 1, this would become 2, and this would become 3. So remember, the 0, 1, 2, 3 is basically 0 is 1 byte, 1 is second byte, second 2 is third byte, and fourth is fourth byte. That is one column of your key matrix. So these 32 bits or 4 bytes basically are copied into W0. Is in W0. Similarly, you just then the loop will be incremented. I would be 1. So the next value that you will store is would be in W of 1, and then in this case it would become 4, 5, 6. Let's take the highlighter. 6 and 7, and then this second column would be copied in W1, and similarly when the I would be 2, its value would be stored in W of 2, and this value would be 8, 9, 10, 11, and similarly for 3, that would be W of 3, and the value would be 12, 13, 14, 15. So in this way, the first 4 words will be copied in this array, right? Then you will move on to this part. And this part basically the loop is being run from I equal to 4 till I less than 44. So that is it will run for 40 times. So basically, and you need to generate 44 keys as well, so that's why it is run for 40 times. So here the logic is very simple. So first that you will take this I minus 1. So when it comes to this part of the loop or this part of the loop code, so value of I would be 4. So 4 minus 1 means 3. So W 3. Here I write 3. So W3 would be stored in temp. W3. W3 would be stored in temp, and then you will check that if I mod 4 is equal to 3 or not, right? So remember in the previous slide they told you that the rest of the words, uh, the, in 3 out of 4 cases you will just do the simple exclusive OR, and in one case you will use a special complex function which is called a G, right? So here your value is 4. So 4 mod 4 is 0, satisfied. So now your temp will be overwrite. How it is overwrite? How is it is overwritten? So your temp would be passed into some function which will rotate the word. Its output will be passed into another function which will substitute the word, and then it will be exclusive OR with a round constant, right? And that would depend on also which round you are. It will be dependent on I by 4, and then this temp will be exclusive OR with Wi minus 4. Here your value is 4, so 4 minus 4 is 0, so that would be W0. So your W0, that is your fourth value down the order, will be exclusive OR with the temp, right? But for the next value, when the I becomes 5, when the I becomes 5, right? So here Wi minus 1 would become 4, it will become 4, that is W4, and in this temp now, in this temp you are going to store W4 now, right? You are going to store W4 now, and since 5 mod 4 is 1, so this statement is false, it will not run this time. And then your temp is W4, is W4, and what will be your let's erase this, what will be your Wi minus 4? So that would be, because I was 5, so 5 minus 4 is 1. So simply the word number 1 is exclusive OR with the word number 4, that is one preceding word and then 4 values down the order and that would be your W5. Similarly you do this for W6, W7, and when it comes to the 8 again, so 8 mod 4 would be 0, and then the temp will be calculated with this value, right? So now we also see this with the help of diagram. Your diagram, you see that you have the original key, 128-bit key, and it is stored word by word. Key 0, that is the first byte, key 1 second byte, key 3 k2 third byte, and k3 fourth byte, and similarly 5 6 7 8 uh, and 8 9 10 11 12 13 14 15. So you have 128-bit key, right? And what you do is that, so for the very first time you just copy the first column into W0 as it is, then to second column to W1 as it is, third column to W2 as it is, fourth column to W3 as it is, right? And from there onwards what you do is that it depends on whether your I mod 4 is equal to 0 or not. So in this case W4, right? So in this case the output will be coming from the G, and it will be exclusive OR with the W0. So W0 is exclusive OR with the output of G. Otherwise, if it does not happen, what happen is, then what you do is that you take the preceding one, the W4, and you take the one which is four down the order, W1, and then you do exclusive OR and you produce W5. Similarly, you do it for W6, similarly you do it for W7, but for W8, what you do is that you will take one input from the output of this G function, and the another input you will take from W6. Similarly, you do it for all your words, right? And we take a look at function G, which is the last part left in our AES. And here you are seeing that so the diagrammatically what is happening, so you have this B0, B1, B2, B3, right? And then it is changed into B1, B2, B3, B0. So that is, they are just shifted one position left, and then you have this substitution, and then substitution produces a new primes, right? And then finally you had the round constant. In round constant you also have, if you notice that these last three values are 0, and only the one column has the value, and then this value is exclusive OR with the result of this column. So let's see a more concrete example. So these are the rules. So first, what you do is that you do the rotate word. So remember in your pseudocode you had the temp, right? So in your temp, so what you do is that you do the rotate word, 1 byte circular left shift on a word. So this means that if your input word is B0, B1, B2, B3, these are all bytes. So this will be transformed into B1, B2, B3, B0. It's just a 1 byte left circular shift. And then you will do a permutation, a substitution, and it is the same as your S box, right? So you take in B1, it is a 8 bits, 1 byte. So first 4 bits most 4 bits will select a row, and the right 4 bits will select a column. And then the result of step 1, 2 is exclusive OR with a round constant, right? And here it is telling you about the round constant. Again, it is using Galois field, so which we are not going into details. So round constant is a word in which the 3 rightmost bytes are always 0. Remember, the value of the 3 blocks were 0. These 3 rightmost boxes or the bytes are always 0. So thus the effect of exclusive OR a word with a round constant is only to perform an exclusive OR on the leftmost byte of the word, right? And only the one box had a value, and which was the leftmost box, right? And the round constant function is different for each round, and it is defined as follows. So this is your table. So if you for the round 1, the non-empty box or the byte with a value will have 0 1, round 2 is 0 2, round 3 is 0 4, round 4 is 0 8, then 10, then 20, then 40, then 80, then 1b, and then 36. And how it is calculated? It has calculated using this multiplication defined over the Galois field, which we are not going into to study, but you can
It is very interesting actually. If you want to study that glass field, it's not very difficult, but it's just that it takes more time, and you can do it in your free time, and it will be very interesting to verify first few bytes in the example. So finally, this is your the whole diagram which summarizes the AES encryption scheme, that you have the 16 bytes or 128-bit input, and first you form the input state. As I told you, IN0, IN1, IN2, IN3 is 16 bytes, and then you do the initial transformation, and then you have the state initial transformation. Then you have the 10 rounds in the from the round 4 till 9. Here it is called round 1 till n minus 1. So you are using 4 transformation, and then in the very last round, which is round n, you are going to use 3 transformation, and then you will have a final output state, and that would be your cipher text. You will also write it word by word, word 0, word 1, word 2, word 3. And then another interesting thing to note that in AES you also have some versions, but the block size of the plain text blocks is always constant. That is 128-bit. But you have AES with a 128-bit key size. You also have another AES with a 192-bit key size, and you also have another AES with 256-bit key size. And AES 256 is commonly deployed. Mostly the banking financial sectors, they use AES 256. So when you see AES 26, it means that it is using a 26-bit keys, right? So that's all for your AES. I hope the lecture was very easy. I would say that it's AES is not easy, but I hope I was able to explain it in a very easier way without getting into too much complex mathematics. And if you have any questions, you are welcome to post on your Google Classrooms, or we can also meet whenever you come in the university. Assalamu alaikum.